Okay, right. I guess I'm streaming now. So, yeah, this is day 2 of machine learning. I guess the first thing to do is go through the flashcards we made yesterday. So the number of computation flops and the processor flops, how can we compute the time needed for a program to run? Okay, so T equals computation flops over processor. Oh, actually, I should turn on my camera. That would be a good idea, wouldn't it? Right. So given the number of computation flops and the processor flops, how can we compute the time needed for a program to run? It would be just the computation flops divided by the processor flops per second. Yep. So easy. Given the number of communication bytes and the channel bandwidth, compute the time for communication. So TCOMs would be communication bytes divided by channel bandwidth. Okay. State a lower bound for training and inference times. It would be the maximum of the computation time and the communication time. So maximum TMAF, TCOMs, I think is the notation I used yesterday. Yeah. State an upper bound for training and inference time. It's the sum of those two. So TMAF plus TCOMs is the worst case. What's the worst case relationship between the upper and lower bound on total communication? I think this is worded wrongly, but from what I recall, we're just saying what's the difference between the lower bound and the upper bound, and well, the upper bound is at most 2 times the lower bound. Yeah, because the worst case is that TMAF equals TCOMs. Yeah. Okay, so let me edit this so that the wording is correct. It will one time. Okay. Define compute bound. From what I remember, there was 2 ways of doing it. So one is just that TMAF greater than TCOMs, and then the other way of saying it is that the intensity of the computation is greater than the maximum intensity, that's arithmetic intensity, of your accelerator. So I think we might have a separate flashcard for one of the other definitions. Yeah. Okay, and I guess it's important to say that, assuming we can perfectly overlap comms and maths, so I'll do that again. Define communication bound, that would just be TCOMs greater than TMAF, assuming that we can perfectly overlap the two. Sure. Define arithmetic intensity, it's the, okay, so I think this again, there were 2 ways of doing it. So one is the flops per second divided by the memory bandwidth, and that's for an accelerator. And then for a program, we're doing the flops required for example, for matrix multiplication divided by the number of, or the total bytes of memory that you're reading and writing. Yeah. Peak arithmetic intensity. So that's the arithmetic intensity when your accelerator is running at peak flops per second. Yeah. Okay. When we have high arithmetic intensity, what's the relationship between TMAF and TCOMs? TMAF would be much greater than TCOMs. Yep. Define compute bound. So that's when TMAF is greater than TCOMs, assuming that TMAF and the maths and the communications can be done at the same time. When we have low arithmetic complexity, what's the relationship between TMAF and TCOMs? So TCOMs is much greater than, or not much, it's just TCOMs is greater than TMAF, I guess. Okay. Find the arithmetic intensity of the dot product of 2 B-float 16s. Okay, so So what do we need to work out? We need to work out the flops and the memory reads and writes. So the flops, we are taking, so let's say they have dimension D, each of the two vectors. For each vector, we're going to have to read in 2D bytes, and that's two vectors, so we're reading 4D bytes. And then we're also going to have to write the result, which will just be a 2 byte. So 4D plus 2 is the total number of bytes that we're like reading or writing. And then the flops, well, we're going to do bfloat 16 multiplications, and we're going to do d minus 1 additions to compute the dot product. So that's 2d minus 1 divided by 4d plus 2. And I guess if you say d is large, then this approximates to a half. Yep. Okay. What are the axes on a roofline plot? So on the x-axis we have the logarithm of arithmetic intensity, and on the y-axis we have the logarithm of the flops per second. Yep. Is this duplicated? Okay, I don't know what went on there. Compute the arithmetic intensity of the matrix multiplication. Z gets xy, where x has shaped BD, y has shaped DF, and Z has... Oh, why is this showing the answer? I'm just going to do it again. What can be said about the batch size relative to the other dimensions? B is much less than D and F. And I think you can also assume that D is roughly equal to F, although not super sure about that one. Okay. I'll do this good because, yeah. So 1024 for B and 8000 for D and F. Okay. So define compute boundedness in the sense of arithmetic intensities. So if the arithmetic intensity of your computation is greater than the peak arithmetic intensity of your accelerator, then your program is compute bound. Okay. Derive a minimum batch size for compute boundedness in transform matrix multiplications. Okay, so I guess okay, I'm going to use a result that I seem to remember, which is that, actually no, I'll derive it from scratch because I'm not certain that I have the right result in mind. So we're going to do what? It's B, D, so a matrix of dimension PD times a matrix of dimension D, F, and then that produces a matrix of dimension B, F. And then so the arithmetic intensity of this computation, let's work it out. So we're going to have BF elements in the final matrix, and for each of those elements we're going to have to do a d by d dot product, so that's 2d minus 1 operations per element in the final matrix. And then for reads and writes, let's see, we've got 2bd plus 2df, assuming this is all bf16. And then we're going to have to write back the bf, so that's plus 2bf. Okay, and now expanding that out, what do we get? So 2bdf minus bf all over 2 bracket bd plus df plus bf. Now neglecting small terms, let's see, product df is much greater, so bdf is much greater than bf, so we can say this is roughly equal to 2bdf over 2df, cancel the df's. Okay, so the arithmetic intensity is roughly equal to the batch size, which, yes, that makes sense, I remember that from yesterday. Okay, and then from there, we want it to be compute bounded, so we can simply say that B is greater than the arithmetic intensity, or the peak arithmetic intensity of our accelerator. Of accelerator. which from yesterday was, I think a value that they used was 240. But obviously this depends on like what accelerator you're using. Yeah, okay, happy with that. Compute the arithmetic intensity of the matrix multiplication. Z gets xy, where x has shape BD, y has shape DF, and Z has shape BF. So we did this in order to work out the previous ones. I'm not going to do that again. Okay, so if you wanted to perform, this is the one that I got wrong yesterday. Int A BD multiplied by, and I think this subscript D means you reduce over D, or, okay, I'm not actually 100% sure on the like mathematical like definition, but I kind of roughly know what's going on. So basically, the way to think about this is you have, instead of this being a matrix, it's like it's a bunch of vectors. It's a bunch of row vectors. It's B row vectors of length D, and then for each row vector, you're going to do the product with a matrix of size df, but then the matrix of size df is like different for every single row vector in this first matrix here. So the number of flops you would do is the same as for like a normal int A matmul, but then the reads and writes, because of this this tensor here being much bigger, you're gonna have more of them. So let's see. So for an a matmul, how many operations are we doing? We are doing BF and then 2D minus 1. Yeah, that's how many operations we're doing. And then for the reads and writes, it's BD plus BDF plus BF. That's the intensity. And then I guess we can simplify here, again using the assumption that B is much less than D and F. So we got 2BDF, neglect the minus 1 factor, over BD plus BDF plus BF. We can basically neglect this and this, so the BD and BF terms go to 0 because they're much smaller than BDF. Then cancel the BDF, so we get, that's got an arithmetic density of roughly 2, which is pretty low. It's definitely lower than the peak arithmetic intensity of our what do you call it, our accelerator. So this will be communication bound, which is like not good. Yeah, okay. When we have low arithmetic complexity, what's the relationship between tmath and tcoms? Tcoms much less than tmath. This is assuming that we can overlap the computation and like reads and writes. Okay, brain fart. I'll have to do that again. What can be said about the batch size B relative to the other dimensions D and F? B is much smaller than D and F. B is about 1,024 typically, whereas D and F are like greater than 8,000. Okay. When we have low arithmetic complexity, what's the relationship between tmath and tcoms? So low arithmetic complexity, that means your communication bound, which means your tcoms is much greater than your tmath. Okay. Yeah, tcoms much greater than tmath. There. Right, so that's the review of yesterday done. Now, on to new stuff for today. So yeah, I guess after reflecting on the work I did yesterday, I realized it's probably a good idea to like make sure I have the basics of like transformers down, because there were some things that they sort of like seem to sort of like gesture at as like, oh, you should, or like they just mentioned without explanation, and I wasn't really sure where they came from. So yeah, I will be going through this notebook, which is from Arena, which is like a bootcamp for like ML stuff. yeah, we'll see. I expect to know some of this already, but yeah, I'll just work for it, question by question. So yeah, let's try answering the question. What makes neural nets more powerful than basic statistical methods like linear regression? Well, neural nets are better than linear regression specifically because they can learn non-linear functions, or yeah. Well, in general, like linear regression is not a universal function approximator, whereas neural networks are. Yeah, I guess that's a sufficient answer. Let's see what they wrote. Yeah. What else? I kind of take issue with this because I mean it's not like linear regression is. I mean I guess you're never you in some sense you're learning the parameters for linear regression, but it's like there's a closed form way of doing it as opposed to neural nets where you're like optimizing towards a solution. Okay, what are the advantages of ReLU over sigmoids? So ReLU, you don't have like vanishing gradient problems. It's also faster to compute ReLU than sigmoid. Yeah. Okay, yeah. Right, linalg. What's the problem in trying to create a neural network using only linear transformations? Well, your entire network can only represent like linear functions, basically. You need like non-linearity in order for like universal function approximation to hold. Yeah. Okay. Matrices A and B have shapes NM and ML. What's the maximum possible rank of the matrix AB? Okay, it's just going to be the smallest out of whatever these numbers is, because I guess the way to think about this is like, so the rank is like the number of like independent rows or the number of independent columns, and they should be equal. And in general, if M is bigger than N, then there can't like you can't. For instance, if like considering matrix A, right? Didn't want to do that. How do I get it to like not render close? Wait. Oh yeah. So like thinking about matrix A, right? If we say that M is bigger than N, then since we know that the number of independent rows and columns has to be equal, then the number of independent rows can be at most, the number of independent, N is the number of rows, right? So the number of independent rows can be at most N because there are at most N rows, and therefore we know the number of independent columns can be at most N, right? And a similar argument for B, and then we also know the product of them, the rank of the product is going to be the minimum of the rank of the like individual two matrices. And I mean, this makes sense intuitively. There's probably a proof for it, which I can't like remember off the top of my head. But yeah, it's the minimum of NML. Yeah. Oh god, I hate that when you click it, it expands this thing. Okay, what's the expected value and variance of the sum of two independent normally distributed random variables, x1 and x2? Are either of these different if they're correlated? Sure, so if they're independent, then the mean of x1 plus x2 is just mu1 plus mu2, and the variance is just sigma 1 squared plus sigma 2 squared. If they're correlated, then yes, it would be different. I'll tell you, I think hold on. I can probably derive this, but I think if they have non-zero covariance, a positive covariance, you can only have positive covariance or zero covariance. And if they have positive covariance, then I think that means the variance of x1 plus x2 is less than the individual variances. Oh, sorry, no, it's less than the sum of the individual variances. Oh, hold on. I guess I should probably go for and derive the variance stuff. Okay, so let's say covariance x1, x2 equals some constant k. So it's 1 plus x2 equals what? And then let's see, how can we approach this? I guess we can start with the definition of variance, which is the expectation of the square minus the square of the expectation. So e of x1 plus x2 squared minus e x1 plus x2, and then all squared. Okay, and then expanding this out, what do we get? Minus, and then let's see. I don't think them being correlated or anti-correlated like affects the mean, but then okay, it says that, but then can I justify this to myself that them having like non-zero covariance will not affect the mean? Okay, I'll just black box that for now, and then I'll come back to it later. Oh, okay, I see. So then the variance of x1 plus x2 is just variance of x1 plus variance of x2. Okay, and then you've got this extra term, which is e of x1, x2 minus 2 times e. Oh wait, no, that should be like this. Yeah, e of x1 times e of x2. That's not super neat, but whatever. Yeah, so that's, and then you add on the variant, or covariance, I guess, cov x1, x2, and you subtract e of x1 times e of x2. That seems a little bit dodgy, because why do I have that extra term? It would be quite nice if it was just like the sum of the x1, variance of x1, variance of x2, and then the covariance. So what's going on here? Oh, that should be a 2 here in the expansion, so that's a 2, that's a 2, and then it's just plus 2 times the covariance. Okay, that makes sense. And then, therefore, if they're positively correlated, then you'd expect the variance to increase, and if they're anti-correlated, you would expect it to decrease. Okay, that makes sense. Right, calculus. What is the derivative of L of xy equals half x minus y all squared with regard to input x? Okay, so partial L partial x equals partial x of half x minus y squared, which equals, let's see, I guess, yeah, it will be a half times 2 times x minus y to the 2 minus 1 is just 1, and then multiplied by the derivative with respect to x of whatever's in there. The minus y part goes to 0, the x part goes to 1, so it's just x minus y. Okay, and then for cross entropy, partial L, partial x equals partial by partial x of minus y log x plus 1 minus y log 1 minus x, which equals minus, and then put that all in brackets. So log x goes to 1 over x, so that will just be y over x. And then log 1 minus x is, the derivative of that is minus 1 divided by 1 minus x, yeah. So that will be subtract 1 minus y over 1 minus x. And I guess we could simplify this further. I'll do that if they do it in the answers, but if they don't, then I'll just check it. What's the qualitative behavior of performing gradient descent on x with these loss functions? So in both cases, you would expect the like loss to be minimized, basically. So in this case, clearly it's minimized when x equals y, and then similarly in this case, it's not like as immediately obvious, but you can consider that y takes on value either 0 or 1, and then each individual term, like you only need to consider case y equals 0, right? This y log x term is going to go to 0. And then here we have just 1 minus y times log 1 minus x. 1 minus y is just 1, so it just becomes log 1 minus x. And obviously that is... So log 1 minus x is maximized when x equals 0, because we're restricting to the range 0, 1. But then we're multiplying by minus 1, so that ends up being the minimum value. Yeah. Yep, x minus y. Okay, and they didn't simplify it, so it's minus y over, yep, okay. And then it's helpful to understand information, entropy, and KL divergence. What is... Okay, I think I know what information and entropy are, but I don't know what KL divergence is. Okay. Yeah, so I guess I will read this article because I have no idea what KL divergence is. It does say that I should know what entropy is, so I guess I'll define that. Entropy is the expected information of like a distribution, I guess, and then we have to define what the information is, and I guess the way of thinking about that is like, or the way I think about it is not information but like surprisal. So like if an event with probability 0 happens, you'd be like maximally surprised because you would not expect it to happen if you've assigned probability 0 to it. And like the other way around, when you have an event that's probability of 1, then you'll not be surprised at all when it happens. And so the information content is basically how surprised you are when you see an event of probability p happening. And then a function that like fits this criteria is like -1 times log p, because when we have p equals 1, then log p is 0, and also minus log p is therefore also 0, so surprisal is 0. And then when we have yeah, p equals 0 or p close to 0, then log p goes towards minus infinity, multiply that by the minus 1, so it ends up going to plus infinity, which makes sense because our maximum surprisal is when p is close to 0. So yeah, so the entropy is therefore the expectation of minus log p, I guess. So I think that's a reasonable definition of it. So I guess we can go read the article. Okay, all divergence is a topic which crops up in it on blah, 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 blah. Okay, so it says maybe just read the summary. Okay, if I read the summary and I think it makes sense, I will move on. But yeah, so 1, expected surprise. The DKLP, I'm not sure what this double bar is supposed to mean given, but then usually that's a single bar, so I'm not sure. Okay. I'll just interpret this to mean the KL divergence of P and Q. Oh, okay, and as I said, it's not symmetrical, so I guess, yeah, we need to say, okay, it's P is always the left-hand side and Q is always the right-hand side. So the KL divergence of PQ is how much more surprised you expect to be when observing data with distribution P if you falsely believe the distribution is Q versus if you know the true distribution. Okay, so it's the expected difference in entropy between so it's the difference in entropy between your actual, hold on, how much more surprised you expect to be when observing data with distribution P if you falsely believe the distribution is Q versus if you know the true distribution. So how much more surprised you expect to be seems like it's talking about some kind of difference in entropy. Okay, so when observing with distribution P, so if you falsely believe the distribution is Q, then you'll get hold on. The entropy, is that not the function of the... Oh, okay. No, so the entropy is a function of the distribution, but then the surprisal, or the sum of surprisal is just something that I guess you would observe as you take more and more samples. If you falsely believe that the distribution is Q versus if you know the true distribution. It would be nice if they had a mathematical expression. I guess I can look that up, but let me just try and grok this. So okay, first of all, it makes sense that this should be positive always, right? Because if Q is not P, then you would definitely expect to make you're gonna always make some wrong predictions about what you're gonna see, or the data will in some way, the data that you observe will not match the what you would predict, and so your surprise level is going to be greater than what it was if you have the true distribution. Okay. Hypothesis testing. The KL divergence of P and Q is the amount of evidence we expect to get for P over Q in hypothesis testing if P is true. When it says over Q, I guess an amount of evidence, I'm not exactly sure like what they mean by this, but I guess it kind of makes sense. It doesn't make sense that the two definitions are like equivalent, or intuitions are equivalent. So yeah, if you're more surprised when you have a false distribution, yeah, if you're more surprised with one distribution than you are another, the distribution that like produces minimum surprise is like probably the one that's going to be correct. So you'd expect to have more evidence for that in hypothesis testing. Okay, maximum likelihood estimators. If P is an empirical distribution of data, DKLPQ is minimized over Q when Q is the maximum likelihood estimator for P. Okay, so holding P constant. If you try out a bunch of different Qs, the Q that will minimize the KL divergence is the maximum likelihood estimator for P. And then, okay, so I guess back to definitions. What is a maximum likelihood estimator? I feel like I should know this, but I actually don't, so it's time to look it up. Right. Okay, so it's telling you the maximum likelihood estimator will, given some observations, it will tell you what the most likely parameters for your distribution are. Right. Back to this. So, but then what I kind of don't get is I thought P and Q were both probability distributions. So how can a distribution also be an estimator? Yeah. I think there's probably time to ask Claude because that kind of doesn't make sense to me. How can a distribution be a likelihood estimator? Actually, also at this time, I should probably check that my mic is on and the stream is like on YouTube somewhere. Can people actually hear this? I don't know. Yeah, I'll turn off my screen for a little bit because I don't want to open YouTube and something crazy comes up. Okay, I'm apparently streaming. This is going to be pretty feedbacky, or actually it won't be. Partial x of half x minus y squared, which equals. I should have probably checked that earlier. Right. Okay. Yeah, so how can Q be a maximum likelihood estimator while also being a distribution? That kind of doesn't make sense to me. Yeah. This still doesn't really make sense, so I will ask what. So I'm going to turn off the screen while I log in. Right. Okay, screen back on. Yes. So trying to understand this intuition for the KL divergence. What I don't get is how can Q be both a probability distribution and an MLE? Because the context with which I'm familiar with maximum likelihood estimators is like from communications. So like, let's say you have a constellation with a bunch of different symbols. Let's say they're real valued signals. Typically, like the decision rule that you would use is like the so like your symbols will basically be like real numbers, and then because of noise, like the actual data you receive is like, so let's say one of your symbols is like the real number 2, but then because of noise you will receive like a 2.5, and then like whatever symbol your like received data is closest to by Euclidean distance is going to be like your maximum likelihood signal, and then the basis of that is maximum likelihood estimators. Like the decision rule is a maximum likelihood estimator for the original signal that was sent, given the fact that you've sent it over a channel with like specific properties. Yeah, so that's why that doesn't really make sense to me, how a distribution can be an MLE. So yeah. Oh. Okay, so you choose Q, which has the maximum likelihood like parameters based on P, and this will give you the minimum divergence. Okay. DKL of P and Q is the number of bits we're wasting if we try and compress a data source with distribution P using a code which is optimized for Q. Okay, this is probably related to expected surprise somehow. So, yeah, because I think I watched the 3 blue 1 brown video on this, but like the like the optimal code based on the like distribution is basically so you know like some prior probabilities about like which symbols are more likely than others, and then using that you can like define some code where the like more probable symbols have less bits. And then it makes sense that if it's optimized for Q, but you're actually sending with distribution P, then you're going to be surprised some of the time, and that surprise will is equivalent to using longer bit symbols where you could have used shorter bit symbols if you had actually just like used the optimal code for P. Okay, I guess that makes sense. 5a. DKL PQ is the amount in log space we can win from a casino game if we know the true game distribution is P, but the house incorrectly believes it's Q. I think this is again to do with surprisal. So yeah. I think this is like pretty directly equivalent to the expected surprise like version, so gonna move on. Okay, 5b seems a little bit more less obvious. We can win from a lottery if we know the winning ticket probability is P and the distribution of ticket purchase Q. Maybe I'm just like not enough of a like degenerate gambler, but I don't actually know why the distribution of ticket purchases is relevant for a lottery. I thought they're just selecting like random numbers. Yeah. What? Yeah, I guess my understanding of how a lottery works is wrong, because I thought they were just like selecting a random like n-digit number, and then if you got that number, you win. If you didn't, you did not win. And so like what other people purchased does not have an effect, assuming that they didn't purchase the winning ticket. Like the only parameter that you care about of the distribution of ticket purchases is whether it contains the winning ticket. But yeah, okay, this is finished. Actually, no, there's one more like ball. Wait a minute. Yeah, I actually don't know what the lottery, how it's supposed to work then. I guess there's another one for Claude. How is the lottery game supposed to work? My understanding was that Q is irrelevant to your winnings because the probability of anyone buying the winning ticket is small. Or there is a single winning ticket. I feel like Claude is getting kind of stupid. Like, I don't think I've ever seen LLM make like obvious typos like this. Anyway, Okay, so it's not a lottery at all. It's just like betting on stuff. Oh, wait, hold on. Is this just a multi-on bandit? I think it is just a multi-on bandit. Hold on. Okay. Okay, so it's slightly different from a MAV. Okay, I'll have to come back to this one because I don't quite understand it. Alright, number 6. You know what? I should have probably eaten before I started stream. Because I feel like I'm like not really focusing on either. But whatever, we're here now. The KL divergence is in some way a natural way of measuring how far Q is from P. If we're using the entropy of the distribution to capture how far away it is from 0. Okay, so I guess the idea that I'm getting from this is like DKL is basically something that looks like kind of like a distance between two probability distributions, but like for whatever reason the DKL of PQ is not equal to the DKL of QP. And actually that's one thing I should probably justify to myself for like why that makes sense. Okay, and that's what they tend to address here. Okay. We care about how much P and Q differ from each other in the world where P is true. Which explains why it's not symmetric. Yeah, I guess if you just like look at it from a sort of abstract point of view of like there are 3 sort of parameters here. So you need to know P, you need to know Q. So yeah, you need to have 2 distributions and you need to identify which of what them is the true distribution. And therefore, based on that, you would not expect the like measure to be like you would based on the fact that it needs to take in those 3 things, you would not expect it to be symmetrical in PQ, because if it was, then you would need to pass in which one is the true distribution. But that feels kind of unsatisfying. This falafel's really good. Yeah, I think I might ask about this. Answer as tersely explained. Why would the KL divergence to be non-symmetrical? Okay, hold on. What is expectation under P? What does that mean? Oh, okay. So I guess if we go back to the definition of expectation, it's a sum of the value. So the expectation of like K under a distribution P is the sum of K, it'll be the sum of like K at index I times the P of K at index I. And then if you're using two distributions, then the expectation under P of like some value is not necessarily equal to the expectation under Q. Okay, that makes sense then. Right. Yep. Okay, so that goes back to what we're talking about earlier. The price or the information is just negative log P. And yeah. Oh, okay. This is actually something I didn't know. The two independent events are exactly surprising as the sum of those events surprisable. When independently measured. And then it's possible to show that those three facts fix the definition of surprise up to a constant multiple. Okay. Could I derive that? Probably. I guess so. Right, pencil and paper time. Or pen and paper time. Right, so right. Oh wait, you guys cannot see me writing. Yeah, this is, hold on, can you see that? Yeah, I was doing working before. That probably looked quite crazy, like I was just yapping at the camera. Yeah. Okay, you probably cannot see what I'm writing, but hopefully it's helpful to see that I am writing. So, let's say IP of 1 should be equal to 0. IP of X, hold on, so low probability events are strictly not surprising. So if Px less than Py, that implies that IPX is strictly greater than IPY, and then also two independent events are exactly as surprising as the sum. So IP x plus ip y is equal to ip x plus y, assuming x, y independent. Okay, and then we want to show that it fixes IP up to multiple. So I guess we could probably start with trying some things like what do you show? Let's say we set y. So let's define, I don't know, beta such that probability of beta is 0. Then IP of x plus IP beta what can we say about this? So equals IP of x plus beta, assuming that independent, and then the other thing, what can we say? So px is necessarily greater than or equal to pb because, or p beta, yeah, because p beta is 0 and probabilities have to be greater than 0 or equal to 0. And then that necessarily implies that IP x is less than or equal to IP beta Okay, and then if we add on beta to both sides, or sorry, IP and beta to both sides, plus IP beta less than 2 IP beta, so IP x plus beta should be less than 2 IP beta. Okay. Has that helped us? Not really. Let's try something else. Define alpha such that p alpha equals 1, ipx plus ip alpha. I guess we should go back to this. So ip of k equals 0. Is that if and only if? I guess I'll assume it to be if and only if. It makes sense that it should be if and only if. If and only if pk equals 1. Alright, so equals ip of x, which equals ip x plus alpha. Actually, it does not seem as easy as I thought, or at least I can't show it. immediately. And maybe this is code, but like I don't think it's that important to know the exact derivation. So that might be something that I'll write down for later, I guess. Actually, there's something I should do. I'll put in the Anki, like, how do I create a definition? Yeah. I guess I could rename this because it's not really scaling book anymore, but okay. MISC to do. And then I guess if I'm feeling in the mood to like derive random stuff, I can do this. So the first one is derive. Or is derive. Show that if must be given by minus k log p subject x, where k greater than 0, given the following conditions or information or surprising, and then I'll screenshot them from the post. There. Oh. Yep. That to do. Okay. So this is a little bit of a failure, but whatever. So we can define entropy as the expected survival, which, yes, mentioned before. Yes, that follows from this. And then yeah, okay, and then the fraction just comes from subtracting logs, which is the same as like, okay. So yeah, I think that expression is probably the most useful thing to memorize. So I'll probably put that and then like also flashcard some like intuitions. So yeah, rename. Oh God. Machine learnings. Yeah. So KL divergence. So define d subscript KL P Q screenshot. And then it's probably also useful to give this form of it, because that's like how you would actually like go about calculating it. Oh, sorry, here. Yeah, okay. So let me look at that so that I can memorize it. So expectation under P of IQ of X minus IP of X, which is the same thing as the sum on X of P of X times logarithm of p of x minus logarithm of p of x. Okay, right. Add. And then some of the intuitions I will also flashcard. State the expected zero price intuition for KL divergence. Oh my god, why is it like cutting out the screenshot earlier? Hypothesis testing, maybe I'll leave that one. I don't know how relevant that is. And okay, why am I full screen? I'm not sure the hypothesis testing one is the most useful. It's also like, I'm coming at this from the point of view of like machine learning, and hypothesis testing is like frequentist statistics, which is not really what we care about. I'll put the Emily and coding ones though, because I like that. I like those ways of thinking about it. For KL divergence. Divergence. I don't know, this seems kind of I mean, they're all a bit hand wavy, but like, I'm a bit skeptical of using it as a distance if it's not like symmetrical. But I guess this is reasonable to understand, and I think it's quite likely that people will use it in that way. I think also the common theme is pretty much a restatement, or I don't know, they seem pretty similar to me, so I'll probably put them all in one flashcard. Intuition for KL divergence. Yeah, I think I'm not going to read further. I'll bookmark. Actually, yeah, no, I think I had a look at this beforehand, and I did already bookmark it. But yeah, I suppose this will maybe come in handy later. Anyway, back to this. Can we answer? Suppose P is the probability distribution of which word comes next, and Q is a language model's estimated probability distribution. What's the cross entropy of P and Q if the model is guessing words uniformly? So hold on, what is the definition of cross entropy? I know what cross entropy loss is, which is like the y log x plus 1 minus y times log of 1 minus x thing from before. So can we? Oh yeah, it's gonna be what this. So I'll write it down. But you have next stream. I'll probably use my digital tablet. I'll have to like fish that out of my like drawers and then use it, and then you guys can see what I'm writing. So I guess the way of doing it is like, given some value of x, what's the we can start with binary classification as a model. So if we have y equals 1, then the entropy in that case is going to be minus log of 1 minus x, because the further away it is from 1, the like more surprised you'd be. Yeah. And then y equals 0. Hold on. Oh yeah, no, so this is y equals 0, and then y equals 1 is minus log of x. Okay. So then, in the more general case, so what is our y? This is like the output of, so y is like the true distribution. So this is like our p. Okay, so, and then it's, so x equals x1, I guess we'll call it, and then x equals x2, and so on. Dot, dot, dot. And then minus log, and then p. So how would I notate this? It's a probability given distribution q. Hold on. Yeah, I'm actually not sure about this. I guess, first things first, let me look up the definition of cross entropy, because I think that's where I'm struggling. Definition of cross entropy, and it's probably worth flashcarding that. Wait, how is this different from? Oh wait, so the KL divergence is just what the? What? Oh, okay. I'll screenshot this, but then I need to review how this is different from KL divergence. HPQ. Oh, okay. And then, so the cross entropy of P and Q is the entropy of P plus the KL divergence of P and Q. So H of P is just what? Expectation of log P under P. Okay, so H of PP is equal to H of P. Right, that I suppose makes sense. And then the KL divergence would then be the expectation under P of log Q minus log P, which, okay, makes sense. Then we're back to like where we were before. Okay, so at that, and then right, going back to here. So the cross entropy, if the model is guessing words uniformly, so that's saying Q is uniform distributed, P is like the distribution of the language, and the cross entropy will then be the expectation under P of the logarithm of Q. And let's see, since Q is just going to be uniform, then we could take the log Q basically out of that summation. So it's going to just be like, because so right, so if we have minus E, wait, if I focus on this, maybe you guys are able to see it better. I know this still seems pretty bad, and if I move my hand, then it's, yeah, quite unworkable. Anyway, so expectation under P of log Q, if we expand that back to the summation form, we get -1 times the sum on x of px times log qx, but qx is constant, so it's just minus log qx times sum on x of px, which we know the sum on x of px is just 1 because it's a probability distribution, so that goes to 1. Then it's just minus log of qx, and qx, since it's uniform, qx has to be 1 over the number of words in the vocabulary, so it's just log words in vocabulary, or hold on, it's the log of words in vocab. And what will the cross entropy be if the model can predict words with exact right frequency? Well, I guess the easiest way to think of this is the KL divergence way. So the cross entropy is the entropy of the P plus the KL divergence, but the KL divergence would be 0 if P and Q are the same. So therefore, the cross entropy is just the entropy of P. So yeah, log vocabulary set makes sense. And it just reduces to the entropy of natural language. Okay. That's cool. I learned something. I'm happy with that. Right, I'll probably flashcard this too because I found this quite instructive. Yeah. I'm not even going to try copy that screenshot time. Yeah, I'm just going to assume that I'm good enough at Python. I would say I'm good enough at Python probably. I'll read what it is they want me to learn. But I feel that I know Python pretty well. So why does this book start with args and quarks? Oh wait, no, it's Python tips, not just Python. Okay, sure. I know what that is. Debugging. I don't think I've ever used a debugger with Python specifically, but I would be, I guess, happy doing that. Generators. I've used iterators, but I haven't written one in Python. I'm comfortable with map, filter, and reduce. I'm comfortable with sets as well. Ternary operators. Does Python even have a ternary? Oh, okay. It has the if else one-liner expression thing. So I guess that's what they're talking about. Decorators. Again, I've used them, but I haven't implemented the decorator. Global and return. Don't use global variables in Python. But yeah, I'm happy with this. Multiple return values. Do they mean just returning a tuple? That seems weird. Okay. Yeah. So yeah, I don't use globals for obvious reasons. And yes, the way they're talking about is just returning tuples. I thought this was something weird. Slots. I've never actually heard of this. You know what? I'm just gonna hope that doesn't matter. Virtual environments, yes, use them plenty. I've used pretty much every single container in here except the name tuple. But yeah, that's because of LeetCode pretty much. enumerate, happy with that. Zip and unzip, happy with that. Object introspection. I think in general I'm probably competent enough with Python to like not go through this. Walking through these 100 basic NumPy exercises. The thing is, I've used NumPy many times before, but it's something that I sort of forget and relearn. So maybe it's worth doing. Wait, hold on. How hard do these actually get? Okay, I guess I'll binary search for the first thing that I like don't know how to do. Find the closest value to a given scalar and a vector. I don't know how to do that. Negate all elements which are between 3 and 8 in what place? Okay, maybe I don't know NumPy as well as I thought. 13. Create a 10 by 10 row of random values and find the maximum and minimum values. I would know how to do that. So what? 12.5 plus 25 divided by 2. We'll just call that like 15. It's a bit less than that, but whatever. Sorry, we'll call that 17. What's the result of this? 0 times nan is nan. Nan equals nan is false. Nth greater than nan, it's false. Nan minus nan is nan. Nan in set nan is false because nan is not equal to nan, and this is also false because of floating point weirdness. Okay, so I should probably do this because I seem to like not know the majority of these. I think this might another one for the to-do because I do want to kind of get through this notebook, even if I don't actually know everything, just to like expose myself to everything. Oops. So go to the to-dos. Complete. To-do. Right. PyTorch, I also basically do not know PyTorch, so I think I've used it like a single time, so yeah. Similarly, yes, God, why did it do this? I'm happy with types in Python and type checking. Yeah, I'm familiar with Matplotlib. I've never used Plotly before, so yeah. This seems kind of like it's an advertisement. Yeah, I'll just stick to my Matplotlib. I'll just say that I'm competent in coding. It's debatable whether I am, but we'll see. Okay, a lot of this seems kind of... okay, why do they want us to use conda? I think like when I was like first ever learning to program, like they were like use conda, and then I couldn't figure out how to install it, and then I just never did that and just used like standard virtual environments. I'm not sure why one would use conda. You know what, I think I'm just gonna say that like I'm advanced enough to like not do this. I will probably just use like Python virtual environments or maybe like UV. Sure, I have WSL on this machine. So it says do the NumPy exercises, do read this thing, read this as well, read this, okay. Seems like I have a big reading list. Okay, and then this stuff seems to depend on the previous. So, what is the time? Yeah, I have a couple more hours that I want to spend on the stream. So, what would be the most valuable thing for me to do right now? I guess the NumPy exercises, because I can probably get through those pretty fast. Well, that's it. I guess I want to finish the rest of my food, so I'll eat it, and then we can get on with the rest of the learning. Oops. Where are you? Never mind. Okay, I'll just close the rest of those. Actually, what am I talking about? It has to do the 100 NumPy after. Okay. I guess we'll just continue on with the notebook and not do the reading. It's probably worth adding stuff to the to-do. And I also need to make a plan to address the items in the to-do, because I don't want it to get to a state where there's just 100 things to do on that. I suppose I should probably check if there's something in the chat. Okay, time again to turn off the screen. I'll be back in a second. Or you can still hear me, but black screen now. Oh, someone did. Sorry. I should wait to respond to that. Hello. Okay. This wasn't very long. Oh, someone did. Sorry. I nice way to respond to that. Sorry. Nice way to respond to that. Some of these, which ones do I think can be good? I think the numpy exercises, there's one about social and some of these, well, it depends on the length, but I'd rather not do the exercises and read what is social and because they require me to know specific things about the library, and I have a feeling that I'm probably not going to end up doing enough high work. Although it depends on the length, but I would probably because I'd rather not do. Well, okay, specifically for the how to get the job done from the lab. I think one of the requirements was that I use Jax, or he recommended to use Jax. And I guess that's similar. Maybe I can do the numpy exercise in Jax instead. But also, it's something that I probably need to do the preparation before stream for it to not be completely boring to watch. Any more boring than it already is. So yeah, I guess I'll start with NLP. I guess that's similar. Maybe I can do the numpy exercise not it's an hour thing. Something that I probably need to do the preparation before stream for it to not be completely boring to watch. I think this is a pretty reasonable thing to read. Some of it I also may already know. I don't think so much. It's videos. That's not really ideal. I much prefer to read things on the transcripts. I think this is a reasonable thing to read. Some of it I also may already know. I don't think so much. It's videos. That's not really ideal. I much prefer to read things.
Natural language processing, or NLP, is a multidisciplinary field combining math, linguistics, and computer. Like the previous ambiguity examples. As humans, we're masters at handling these ambiguities because of our experience and the...
Yeah, I think this will have weight.
Natural language processing, or NLP, is a multidisciplinary field combining math, linguistics, and computer. Like the previous ambiguity examples. As humans, we're masters at handling these ambiguities because of our experience and the...
So I'll probably go through flashcards and then maybe answer. Seems a bit short for time, but...
Natural language processing, or NLP, is a multidisciplinary field combining math, linguistics, and computer. As humans, we're masters at handling these ambiguities because of our experience and the...
So I guess there's the cross-entry way of defining it, which is H short P Q equals HP plus D K L. And then the other way is just the direct definition, which DKL. So I guess there's the cross-entry way of defining it, which is H Q equals minus C excitation P of the information Q of direct definition which detail x minus x, and then if we go through and actually apply the definition of information, then, or actually no, there's no minus in here, it's just positive, and then it goes QP, Q of direct definition which detail x minus and then if we go through and actually apply the definition of x, or actually no, there's no minus here, x, and then I suppose one thing we can do is bring back the minus in and reciprocate it, so it's expectation under P of log x over x. Sure. And yes, I'm happy with this. Activate the expected surprise intuition for KL divergence. The KL divergence can be thought of as the difference in expected surprise between so you've seen the true we say the true distribution is P, and if we believe falsely that the distribution is Q, then the KL divergence will be the difference in surprise between what we get, assuming that the distribution is Q, and the expected surprise that we would get if we had the correct belief, which is that the distribution is Q. Yeah, I think that's a reasonable explanation of it. Defines detail PQ. Well, I should have clicked good because we have already done that. If we had the correct belief, I should have clicked EP. Same thing. I guess I'll do the rest of the KL divergence. So the ML intuition for KL divergence. So the KL divergence is minimized. So you fix and then the value Q which minimizes KL divergence is the maximum likelihood estimated ML, which is to say, if Q is some like parametric distribution, then the most likely values of the parameters the most likely values of the parameters based on the data they can infer from P will give you if Q is some like parametric distribution, yeah, the most likely values of the parameters right. So optimal coding. So the KL divergence is a measure of the difference in the length of the encoding if you're using a suboptimal code which assumes a false distribution Q versus if you use the optimal code which assumes the true distribution P. So the KL divergence is a measure of the difference in and then Bregman divergence is basically saying that in some sense KL divergence is measuring sort of a distance in quotation marks between like what we believe to be the distribution Q and what the actual true distribution is P. And then Bregman divergence is basically saying that I guess this is also the mention that if we use entropy, so to define cross entropy HFP. So right strum H is the negative expectation under P of log Q. Suppose P is the probability distribution of which word comes next in natural language, and Q is the language model's estimated probability distribution. What's the cross entropy if the model is guessing words uniformly? So we have P minus E under P log Q. probability distribution is which word comes next?
Oh yeah, and then we write it as a summation, so this is minus x px log 2x minus.
We know that qx is just one of the vocabulary size, and it's a constant on x.
So we can just put that as log p, write it as a summation, so minus x of px,
By definition of probability, sum of x on
x
on px. It's just one, so it's just the logarithm of qx's vocabulary size. And then if the model can predict words with the exact right frequency, then the cross entropy is just the same as the entropy, because you have tail divergence of 0. We know that the tail divergence is just the difference between the cross entropy and the entropy.
it's just one, so it's just the logarithm of qx's vocabulary size.
So regular divergence is basically saying that if you use entropy as some like. Oh, okay. Now I see what it's saying. So it's going back to sort of the cross entropy and entropy, right? So if we think of like entropy as like some sort of positional measure of like of the distribution, then the tail divergence in some sense is the distance, but obviously it's not symmetrical. If we think of like okay, I think I'm happy with that. As like some sort of positional measure of like these are so often we'll put in integration for KL divided. So the KL divergence gives the number of bits between the length of the encoding if you use the code optimized for false distribution view, but your actual data is your distribution KLXD. And you would expect it to be longer if you use your suboptimal code. Bits between the data ML is the intuition of KL so if we take Q to be some parametric distribution, then the value of parameters which cause the KL divergence of Q to be minimized are the maximum functionality parameters of Q given the distribution Q to be some parametric distribution. Value of parameters which cause the tail divergence define cross entropy H so minus 1 times the expectation under P of P of distribution. So the cross entropy will be the log of the vocabulary size, and the cross entropy if it can predict whether that correctly is just equal to the entropy of the language itself. Cool. Cross entropy will be the log of the vocabulary size, and I think that's probably where I'll end it for today. I wonder how long that recipe is. It doesn't feel like very much. Wow, it's just like. Oh, we should probably not do this because it's going to cascade into the. We've been on for about 2 hours, I think. Alright, yeah, I think I'll end it today. Tomorrow, I'll probably figure out like what I'm actually going to do next after I finish the stream. And then tomorrow will just be sort of reading, probably doing some. I feel like I can do a lot of so maybe I should like write some code and actually to do that because like because we need stuff I literally have on like a line of code and a couple of blocks and I should probably do that. Yeah. Reading and stream. Bye. See you tomorrow.